All right, hello everybody, and welcome to our unit on probability and statistics. This particular video is going to cover the introduction and getting ready section to take on this unit. First of all, the one thing I do want to mention for you guys is probability. Probability is something that you guys haven't seen much of before, but just to simply define how you calculate probability, it is going to be the proportion of number of successes divided by the total number of outcomes. Okay, so if you're ever calculating probability, you can say P for probability is equal to the number of ways to succeed, we'll just say number of ways to succeed divided by the total number of outcomes. For example, if I was trying to calculate, or if I was rolling a six-sided die, and I was trying to calculate the probability that I was going to get a roll a one, I would say, well, how many ways are there to succeed rolling a one? Well, there's only one way to roll that one, so that would be one way to succeed. And then how many total, what are the total number of outcomes? Well, I could roll 1, 2, 3, 4, 5, or 6. So there are 6 total outcomes. So the probability of rolling a 1 would be 1/6. In fact, you would probably write it, if this was a function or something like that, you'd probably write P of 1 is equal to 6. Something like that. But anyway, if you wanted to figure out the probability of rolling a 1 or a 2, then it could look something like this, like the probability of rolling 1 or a 2. Again, notation could change here, but anyway, but it's still the exact same. How many ways can I succeed? Well, I could roll a 1 or a 2, and those are two different ways. What are the total number of outcomes? Well, I could still roll a 1, 2, 3, 4, 5, or 6, so that's 2 out of 6, and that would simplify to 1/3. Okay, so the probability would be 1/3 or 0.3 repeating. Okay, all right, so just to get that out of the way, in this unit we're mostly going to concentrate on statistics, and so let me scroll down here, and yeah, I'm just going to read through this real quick. In this unit, you will investigate whether a normal distribution is an appropriate model for data. So that's going to be really important, whether or not it is normal, because data can be distributed in an infinite number of ways. And if it's normal, it has a special look, and it has specific properties that we can extract. But anyway, if it is normal, how to use the model to analyze and understand the data. You'll learn the importance of impartiality in surveys and experiments, as well as use simulations to decide whether data are consistent or inconsistent with a particular conjecture. You will also investigate how to use data from a randomized experiment to compare two treatments and decide if an observed treatment effect is statistically significant. All right, so I'll scroll down and take a look at some of these terms, and I'll just kind of briefly touch on each one of these. Some of these you may have heard of, some you may have not. All right, so as far as academic vocabulary goes, we have placebo and simulation. You may have heard of the placebo effect before. Actually, let me change this to a this thing's starting to slow down a little bit, but anyway, so placebo effect. Okay, and so just to describe that effect that you may have heard of before, um, typically in an experiment, you might have like 100 different people, and maybe you're testing out this pill to see if it really works. Well, you're gonna give all 100 people a pill, um, and but like 50% of them you're gonna give a placebo pill. So like a fake pill essentially, and then you're gonna sit back and take in the data and see what happens there. So the idea is to eliminate bias, and and so everybody kind of thinks they're taking the pill no matter what, when really, 50% are taking the actual pill, and the other 50, it could be like some kind of sugar pill or something or whatever. So anyway, we'll talk more about that as we go on. Simulation. So a lot of times we might want to simulate a particular um, thing happening, and this is particularly prevalent today because we can simulate. You don't have to have a computer to simulate, but typically we use computers to simulate because they can do these things very fast. So, for example, I could literally sit there and flip a coin a million times, right, and record it, and then do the math with the data that I get. Or I could just write a quick little program on in a computer, and it could simulate that happening a million times, flipping a coin a million times in like a split second, for example. And then bam, I got my data right there and ready. So anyway, and we'll use some simulations, some computer simulations when we go through this. Anyway, math terms, density curve. So there are these, it's a whole class of curves in mathematics called probability density curves or probability density functions. And they're pretty similar actually to what you guys are used to in regression analysis, meaning like the line of best fit, for example. So, like, if I go off to the side here, and this thing's slowing down quite a bit, but if I go off to the side here and I have some data points like so, you guys might say, oh, well, I can fit a line, right, that to that data. And that way I can kind of throw away the data points and I can just use the line, the equation of the line or the function of that line to start answering questions like what's going to happen out in the future, or I don't have a point right here in the middle, but if I did, have an x, what would the value of the y be? That kind of thing. Now, probability density functions work a little bit different. Let me undo these. So the way that it works is, again, you can kind of think of this as a y as well, but essentially what you're doing is you're kind of plotting all of your points as what's it called, a dot plot, and so you're just kind of piling up the data like this, for example, and what you're doing is you are then going to fit this curve on top of this data, and you're going to say, well, 100%. Sorry, my mouse is very slow here. 100% of the data fits underneath this curve. So again, you can then throw away the data and just deal with the curve. And then what we do is we slice this thing up and we say, okay, well, if 100% or and not the same thing as 100% is the number 1. If the area underneath this curve is 1 or 100%, then how much area is between this x value over here and this x value over here? Okay, then we can start answering, well, if there were, a million data points, then, and we know the percent that was from this x value to this x value, then we can then figure out how many data points were underneath there, or make predictions and all that kind of stuff. So these curves can look like anything. We're concentrating on one specific density curve called the normal curve. All right, it's also called the bell curve, and actually let's come back over here because that's going to bring us to these points. So if data is normally distributed, or close to normally distributed, as this data actually is, we can apply the normal curve. There are other names, many other names for this normal curve. It can be called the bell curve. That's very, very common because it looks kind of like a bell. And you're going to see that this is not a particularly great drawing here, but you'll see a lot more of these as we go through this unit. But it can also be called the Gaussian curve or Gaussian function. There are quite a few different names. And it does actually have a mathematical, what do you call it, a function. Maybe I'll show you that really quickly. We'll say Wikipedia, normal, we'll just say normal distribution, that's fine. And if I go to here, I'm sure they're going to give us this function, and there it is. So yeah, so you can see this thing can be stretched. Here's the bell shaped, and it can be moved anywhere based on some of these values. Specifically, it's based on the mean in the middle, the average in the middle, and this thing called a standard deviation, which measures how far it's spread, essentially the data. But this here is that function, and um, so theoretically, you could actually answer these questions as what's the probability from, or what's the area under the curve, which will give us probability from a certain x to a certain y. But in order to do that mathematically, you would have to do something. Well, you'd have to do some calculus on here, and this would actually be some fairly tough calculus, not very standard, I should say, not elementary calculus. Um, and essentially you'd be taking the antiderivative or the integral of this thing, if you know what that means. But anyway, we are not going to worry about all of that because this is an extremely important concept. So you guys are just being exposed to it, the normal curve. But at the same time, we're not expecting you to do any calculus. In fact, it's so important and so common that we have tables that will, instead of you doing the calculus, you can just look up these values, which I'll talk about in a second, a little bit later. Okay. All right. Let's go back here and continue. Let's see. So we have sample surveys, responses, different ways of collecting data. There's a lot of different ways and methods or modes or whatever you want to call them of collecting data. For example, experiments. Within that data, we need to know what's the explanatory variable or response variable. A completely randomized design is very important when we're collecting these data and designing our methods of collecting the data. Randomized block design, matched pairs design, single blind study, double blind study, observational study, simulation. So all these are different ways of collecting data, and then they're kind of sprinkling in some other words here as well. Like for example, bias. We want to try to eliminate as much bias as possible. That's a really important goal when we're collecting data because your data is only good if if it actually represents something real, and if it's already biased, then it doesn't really matter what kind of math and predictions you make on it. It's not valid. So a simple random sample is really important. That's something that we try to achieve. It's like this goal when we collect the data. Is it a simple method and is it random? And actually, let me come back up here to sample. So very typically, it's not feasible for us to collect the entire population's data. And that's why we have statistics, by the way. So, for example, if I was trying to figure out the average weight of a tennis ball in the entire world, right? I could figure out what we would call the true mean or the true average by finding every single tennis ball and measuring it, and then coming up with the average. But that's not feasible, right? There's no possible way I could do that. But would it be good enough to just take a sample of tennis balls? Maybe and then we have to talk about, well, how much is enough? Is 10 tennis balls enough? Is 100 tennis balls? 1,000? 1,000,000? 1,000,000,000,000? At what point is it good enough, a big enough sample, and it's also not too large for me to not be able to to handle that? Okay, so those are the types of things we'll discuss. But anyway, let's see here. What else do we have to talk about? Oh, confounding variables are extremely important. Another name for this is a lurking variable. And a lurking variable is a little bit more descriptive of than confounding. So basically, when you're designing a way to collect data and analyze it and all that kind of stuff, you have to be thinking about confounding or lurking variables. You're trying to eliminate these variables from your study. These types of variables, if they're not taken account, if they're not accounted for, then you could come up with some kind of, amazing experiment or whatever, some kind of study where you really think you've proven, hey, this correlation between this measurement and this other measurement is it's like 100%. So you could almost say X causes Y, right? And but then, when you publish or whatever, your peers might point out, hey, actually X doesn't cause Y. It's actually Z that causes Y, and you did not account for that in your study. And that would be known as a confounding or a lurking variable. So anyway, um, and that brings up another really good point that I don't see, unless I'm missing it, I don't see correlation and causation in here. And one of the things we're trying to prove when we do statistics is causation. It's kind of like the holy grail. Um, and in order to do that, we need to go through correlation first. So, and again, I apologize. This is going to be very slow because my mouse is very slow at this point. So I'm just going to go slow without screwing this up. So correlation, does that imply causation? Give me 1 second. Whoop. It's very slow and laggy. Okay. So what does it mean to be correlated, first of all? Well, if the curve or whatever, if the curve or the regression model or whatever, if it very nicely fits the data, then you might say it's very correlated. All right, and I'm gonna kind of scroll down and show you what I mean by that. So, for example, let's see how this goes. If I have this data like that, and then I went ahead and figured out the line of best fit, there is an actual measurement called R, which is the correlation of the line of best fit and the actual data points. And it basically tells you how well the line or the curve or whatever it is fits the data, because it could fit it well or not. And so, for example, something that would not fit well, and maybe this R value, let me just give you an example, could be like 0.9, I don't know, 7, something like that. I'll talk about what that means in a second here. And you might have the exact same line. See if I can kind of replicate this, right? Because you can always calculate a line of best fit. But this data was more like this. All right. Is this the best line that fits that data? Yeah, definitely, right? But this R value might only be like points, I don't know, 1, 3, whatever. Okay. So ultimately R, we're kind of getting a little bit off topic here, but it's important to link these concepts together. So R is going to be between -1 and +1. Okay. The negative signifies a downward slope. The positive signifies an upward slope. But ultimately, the closer to 1 or -1 R is, the better it fits the data, as you can see over here with an R value of 0.97. Okay. The R value over here is closer to 0. So the closer to 0, whether it's negative or positive, the closer to 0, the worse fitting it is for that data. Okay? So that is correlation. Now, when I scroll back up here, correlation does not imply causation. Just because this X really is correlated to the Y value does not necessarily mean that X causes Y. Okay, we make that mistake all the time, especially on the news. But it is it is actually extremely difficult to show that, or to jump, I should say, from just a correlation to showing that something causes something else. Okay, so just keep that in mind. All right. Anyway, kind of a little bit off topic there because we're not going to talk about these values in this particular unit, but they are linked. So anyway, all right. So let's scroll down a little bit because I think we've basically gotten through most of this. There's some things I didn't talk about, but we'll talk about these as we go through this unit. All right. So here we go. Let's see here. So we're going to go through these very quickly, and I'm mostly going to do this side on the calculator just talk a little bit about it. So the following are lengths of time in minutes that it took each member of a group of 12 running buddies to complete a marathon. So I'm going to come over to my calculator, and I'm sure I'm going to have to reload this. Let me just check and see. Yes, I do. Give me 1 second, and I'm going to load. It'll just take a minute here. There we go. Okay, so we're going to use our calculators quite a bit, and so I'm going to first go into stat because that's where we enter data into lists, and I'm going to hit edit. And you can see there are a bunch of lists where I can edit or I can add data into these lists. So I'm going to go ahead and start punching in this data. And actually, one of the biggest mistakes students make during this unit is simply not typing things in correctly. Like I just typed in that 229 really quickly and only 29 popped up. So you need to really make sure that you type in everything correctly as you go. 230 looks good, 234, 215, 231, 239, and again I'm checking every single one of these to make sure it's correct. 239, 229, 221, 231, 220, and 238. And I also always make sure I have the same number. So right now I'm on like the 13th, and there are so there's nothing in the 13th spot. So I must have 12 numbers here, and there are 12 numbers here. So we're good. All right, so real quick, how do I make a stem and leaf plot using this data? Let me first of all go ahead and I'm going to, I guess this is reset, so it's fine. So let's go to stat plot, which is right above the y equals. So second stat plot. And you have a series of plots that you can turn on and off. And I'm just going to hit enter to go into the first one. And I'm going to turn it on first of all. And then I'm going to go down and choose what kind of plot it is. And so there are two types of stem and leaf plots, and this one includes outliers. This one does not. If you can, I always choose the outlier one unless they specifically tell me not to. So I'm gonna check that one or hit enter. We're gonna say which list of data we're using, which is list 1. That's where I put my data. Frequency, usually just leave that as 1, and mark, you can choose whatever marks you want. And I'll hit actually I'll hit graph and nothing pops up. Well, why does nothing pop up? Because this graph actually is turned on and it actually is in the graph. It's just that my window is not in the right spot. These numbers are going to be along, the x axis at like 241, 229, those types of things. The good news is with statistics, it's very easy to encapsulate the data by just going to zoom. And if you go down to number 9, there is zoom stat, so you can just hit enter there or just hit 9 for to go straight there, and there you go. So it automatically zooms, and you can trace through this, which basically gives you the minimum. You can see it down here, 215. Here's quartile 1 at 225. Here's the median at 230.5. Quartile 3, 236, and then the max there at 241. All right. Make a dot plot of the data. I am going to talk about that actually in a second. Our calculators don't really make dot plots. They can do scatter plots though, but the dot plot is kind of actually what we're after, but it's very similar to the histogram. So you can really say either dot plot or histogram. So let's go ahead and make a histogram. And actually, I am going to just go to stat plot, and I'm going to go back into number 1. And I'm going to change this, let's go down, to a histogram right here. And so I'm going to hit enter. I'm going to go back to the graph, and it's going to look kind of strange. Let's go back and do another zoom, and then number 9 for Z stat, zoom stat. And you're going to see, there we go. We got a nice histogram. And if I trace through this, right here is the trace button. you can see for each bar, it will tell you the range, right? This goes from 215 to 220.2, and there are two of these values inside of that range to give that bar, right? The height of the bar. Here's this range, and then n is 1. Here's this range, 3, so on and so forth. Okay, so there you go. Describe the distribution. So when we describe the distribution, we're talking about what this data looks like. Okay, and I don't know. I mean, if I were to draw a curve over the top of this or to fit this, I would say it's kind of somewhat bell-shaped. All right, there's not a lot of data here. Okay, that's part of the problem, but anyway, it's kind of hard to describe this a little bit. You know, it's a little bit higher all the way on the left. It kind of tapers off on the right. You know, you can lose a lot of words to describe this, but ultimately, we're not usually using this little amount of data. We usually have a much larger amount of data, which gives it a better shape, by the way. And we'll talk about those shapes in a second. All right, use technology to determine the mean and the median. So I'm showing some graphs here. Actually, a lot of the time we don't even really look at these graphs. We just care about the numbers. And so if I quit out of here, and I remember I do have this list. It still exists down in here, and I can do whatever I want with it. I'm going to go back to stat, and if I go to calc, so I'll go to the right, there are these one variable statistics that pretty much tells you everything about this particular data set. So I'm going to hit enter, and which list do I want to calculate one variable stats with? Well, it's list 1. Doesn't matter about frequency. I'm just going to hit calculate here. And you get all kinds of data here, and if I scroll down, you'll see there's even more. All right, so let me scroll back up and go through this very quickly. This is the mean. That X bar is the mean of this particular data set. So 229.83 repeating. This is a summation. So if you added up all of the X's, this is the uppercase sigma. But anyway, that means summation. So adding up all the X's, you'd get, if I added these up, I get 2,758. Sometimes we actually want the summation of the square of each of these. It's particularly important with like negative numbers, but a lot we do have, like if you took like AP stats or something like that, we have a lot of equations or formulas, I should say, that require this value. So sometimes it can be useful. It won't be useful in this particular unit for us in our class. We have two standard deviation estimates here. Well, yeah, I guess ultimately all stats is estimates. So this one is for this sample, S for sample. Okay, so the standard deviation, which the standard deviation measures how spread the data is around the mean, okay, around the average. So this standard deviation is 7.9, and this is an estimate of the actual population, okay, which is a slightly different calculation. So not the sample. All right, so if I was using the sample to try to estimate the standard deviation of the population, it would look like this. This is actually a lowercase sigma, this little symbol here. But anyway, you can see it's slightly different. N tells you the number of data points, which is 12. We have the min, we have quartile 1, the median, quartile 3, and then we have the max. Okay, there we go. All right, let's go ahead and I'm going to go down and I'm just going to talk about a couple more things here, and then we're going to kind of try to wrap this up. So first of all, the normal distribution, I told you guys it looks like a bell curve, kind of like that, and we usually just list our x-axis, sorry, and we can say, like, in general, again, you can have an infinite number of curves, but in general you can have a skewed, this data can be skewed or have a skewness to it, and it could look like this, or it could look like this. Okay, so I'm going to draw these x-axes, and again, let me just put some points in here. It might take a little while because this is so slow. Actually, let me use my mouse because it's a little bit quicker. So again, maybe you're like piling up all this data. Oh, there's lines there. Well, that's okay, whatever. All right, but ultimately, you know, you're doing these dot plots, essentially, right? And so all of this data is getting stacked up at a particular mean value, which I'll call x bar here, obviously the average is going to be right in the middle of all of that data. Are you going to have data points over here? Yeah. Are you going to have data points all the way over here? Yeah, but there aren't going to be that many, right? And so this is what we would call a normal distribution. Has this bell curve, normal. Okay. And over here, you might have kind of like a lot of the same points. I should really these are really small points, so I apologize for that, but that's okay. So all these points are getting stacked up here. And then, so it kind of has this bell curve, but then you might have a few of these, they might even be outliers, a few of these points way out here that are kind of pulling this to the left. So actually, students make this for some reason in our brains, right? It's just like if I asked you, is this skewed to the left or to the right? Your brains automatically go to the big mound here, and they're like, it's skewed to the right. But that is actually the opposite of that. This is skewed to the left. And the way that I always envision it is I go back to the normal. Well, if it was normal, right, it would look like this bell curve. But if I were to skew it to the left, I almost imagine like me pinching the sides with my fingers. I like take my fingers up here and I'm like pinching this right here, and then I'm pulling it over to the left. And that's what these data points are doing. They're pulling it to the left. So this would be skewed left. Skewed left. Okay, and so this here would be skewed right. And as I write, everything's slowing down, so I apologize here. Skewed right. Okay. And it's important now to talk about measurements of central tendency. Okay, and there are 3 measurements of central tendency. We have the mean. Whoops, mean. We have the median. Whoops, let's do that. Median. If I could spell here. Hold on, let me just undo that. Is it going to do it? There we go. Median. Again, I apologize again. This is taking forever. My computer's acting very slow. And we have the mode. And that one's not even going to write. Let's see if I can get it to write. There we go. Mode. Okay. And so these are measurements of central tendency. And what I'm actually going to do to avoid writing here is I am going to, let me see if I can bring up, I already have this kind of written out a little bit. Bring this over. Here we go. So these are some old notes here. Let me zoom in. So in a perfect world, right, which would be a normal distribution, by the way, if you measured the mean, median, and mode, they would all be equivalent. Okay, they are all the same if it's completely symmetric, right? The mean is right in the middle. The median is right in the middle. The mode is right in the middle. And we're going to talk mostly about mean and median here, but imagine, and again, forgive me, but imagine that you just are working with these blue numbers here. 1, 2, 3, 4, and 5. So this is my data set. And if I ask you, well, what's the mean? You would say 3. 1, 2, 3, 4, and 5. Add them up, divide by 5, and it's 3. That's the average. What's the median? The median is the middle. Well, 3 is all, that's also 3, right? Is the median. The mode is something slightly different, right? That's where we have what do we have the most of. So we're not going to talk about that right now. But I want you to imagine if I change this 5, cross it out, and this became 100. And what changed, right? Well, did the median change? Did the middle change? No, it's still, the middle value is still 3. Did the mean change? And the answer to that is yes, it changed by a lot. If I calculated the average of 1, 2, 3, 4, and 100, right, that 100 really pulled the mean a lot over, okay? So what's more appropriate to use, right, for a data set? What represents a data set better? Well, in many cases, actually the median, right? Because you might say this 100 is an outlier, right? And it shouldn't really be considered. But in the real world, like, just because it's so easy to calculate, I think maybe, I don't know, but we tend to always refer to the mean or the average, when actually a lot of times median is more appropriate, because again, it's all about what represents the data better. So in a perfect world, these three are all the same, right? And so in this normal distribution, actually let me use my mouse because it's working a little bit better. All three of these are right in the middle here, right? But when something gets skewed, and I'm going to use my mouse, so this is going to be kind of bad here, pulled to the left, right? One of these never changes. One gets pulled a little bit, and the other one gets pulled a lot. Okay, now the one that doesn't change is the mode, because we still have, like, if you look here, we have the most data, right? The biggest number is going to be right in the middle. So I'm going to do this with my mouse here. We'll say mode. Okay, actually, let me grab my pen, even though it's going to be slow. The one that gets pulled the most is the mean, the average, as I just showed you. And then the one that gets pulled kind of in the middle might get pulled, might not, but that would be the median. Okay, so it's kind of important to understand these concepts of measurements of central tendency, the mean, the median, and the mode. And as we have introduced like a skewedness, how those can get pulled. Now that being said, in this particular unit, we're mostly going to be just dealing with normal distributions, which makes it nice and easy. Okay. All right. Let's see here. And lastly, we actually already talked about this. Suppose that 12 families with one child each were surveyed and asked these questions about how much time in minutes do you spend reading to your children, or did you spend reading to your children last week, and then how tall is your child? If a strong negative correlation were observed in a scatter plot, where the x-axis would be reading time, the y-axis would be height, would that imply that reading to your children stunts their growth? All right, and let me bring that up here, if I can. Oh, I guess I don't have it up anymore. Yeah, maybe I can bring it up right here. This is from an old answer key, and it's just quicker to bring this up here. So let's see here. Okay, so I'm going to zoom in, and I'll kind of move off to the left here. So here we go. Disregard all this other stuff here. Just in the box, what do we have? Well, we have reading time, and we have height, and they're saying there's a strong negative correlation. Okay, meaning the slope is downwards. So this would infer like it's heavily correlated. So does reading to your children more stunt their growth? That's the real question. And again, does this correlation imply a causation, right? And the answer to that is obviously no. Now the data might show that some kind of super strong relationship, right? But we know in the real world, right, there are many other variables, confounding variables or lurking variables that cause height to go down, right? And if you did, what could cause this part? Maybe there's not enough data or whatever. But obviously, we know that these two are, one does not cause the other for sure. But it just so happened in this particular data set, they're saying that we had this strong correlation. So again, there could be many faults, right? Or there might not be faults at all. Maybe there is a super high correlation, but we still cannot say that reading time causes stunting in growth, right? So there are many underlying factors there. Okay. All right. So we are going to let me get back to this. That concludes our getting ready, and I do want to show you a couple of more things that are, can hopefully help you as we go through this unit. So I'm going to go over to my other screen here, and this was actually yesterday's lesson. So, but anyway, so this is in our calendar. It's lesson, I'm calling it 36-0. It's the before the first lesson. So this is our introduction. So I have a few links here that I would like you guys to explore. The first is a bell curve simulation. So how does that thing get created? And I'm actually gonna kind of like turn this thing on right now. And you guys can play with this, but I'm going to increase the size. I'm going to also increase the speed and restart this thing. There we go. And I'm going to kind of let this thing run. This is kind of like this game. You know, sometimes you've probably seen it on TV. I think it's called like Plinko or something like that in a popular, very old TV show. But you can actually see as these get dropped, you can see this curve or the data starting to pile up. Now this is one particular case, but I want you to go back to imagine, you know, if we were grabbing all of the measurements of the weights of a tennis balls, right? So every tennis ball we're measuring. Well, obviously there's going to be some kind of true average that exists out there. Are we ever going to get that true average? No, not from a sample, but we can get close to it. And basically, the bigger the sample, the closer we should be getting to that true average, which would be in the middle of this data set. But you can kind of see here, it's already starting to form this bell-shaped curve, okay? So I'm going to stop that, and we're going to, again, you can play with that. Let's go to the empirical rule. So once we say, yes, it is normally distributed, we can apply this amazing rule called the normal empirical rule or normal model. But basically, it's the 68, 95, 99.7 rule, which essentially says, well, in your sample, here's the zero value is the mean, and then we can calculate this standard deviation over, which or we can calculate the standard deviation, right, which tells you how spread the data is, and then you can go, well, within one standard deviation over, which would be from within one would be from -1 to +1. It actually turns out that 68%, approximately 68% of the data fits inside of here. Okay, so yeah, if I have really just those two numbers, all I need is the mean and the standard deviation, right? And I can estimate, you know, the number, the percentage, and then from there the total number of data points that are inside of here. The 95 would be from within two standard deviations, so from -2 to +2, and then 99.7 that would be within 3 standard deviations. So 99.7% of the data fits inside of there. Now the total area is 1, so these go on actually to infinity, negative and positive infinity. It's just a very, very, very small piece, percentage, 0.3% of that data fits on the outsides there. So this is actually very interesting because you can answer a lot of questions just by in your head, right? Just using this rule. And you'll have to do that during this unit. You'll have to answer questions using the empirical rule without a calculator. And then you will also have to do it with not using calculus, right? But using the Z table, which let me go to that. I'll go to that Z table in a second here, but I want to show you what that looks like. Bell curve calculations. And if I scroll down here, there's a lot of information. You guys can read that, but I mostly just want to show you, okay, here's a distribution. Here's the mean value, and this is actually the population mean. But if I move this left and right, you can see the whole distribution is changing because it's surrounding that true mean value, okay? And I can also change the spread or the standard deviation. So, right, the bigger the standard deviation, the more spread the data is out. The smaller the standard deviation, right, the closer it is to that particular to that mean value. Basically, you'll also notice that very typically the more data you have, the closer and closer and closer it's going to get to the mean, because it's going to get more and more accurate. And your standard deviation is going to get smaller and smaller and smaller. Okay, so but anyway, let me reset this. Now this little green area, so I have these green sliders, so you can actually measure the probability or the area under the curve from a specific x value to another x value. All right, and the way that we do that is either with the empirical rule. You can see these dotted lines are the standard deviations. So I could say, well, if I'm going from this number, whatever that happens to be for this data set, to this number, well, that's from -1 standard deviation to +1 standard deviation. Oh, I know, based on the empirical rule, 68% of the data it lives in there. All right, and say I, had 100 data points. Well, I'd say 68 of them should be inside of here. That kind of thing, right? So we can answer those types of questions. And based on that rule as well, you should be able to say, well, 68% is here, 95% of the data is here, and this thing is symmetric, right? So if 68% is here within one standard deviation, well, how much is here? Well, that would actually be exactly half of 68%, so 34%. Or you could go even further and say, well, what is the percent inside of here, right? Well, this overall is 95, this is 68, so take, 95 minus 68, but then that would give you this here and this here, so divide that by 2. So that kind of thing, right? Now, that's the empirical rule, but in many cases, we want more accurate descriptions, so we are going to use this thing called a z-table, where we could figure out their z-score, all right, of these values, which essentially is like this normalized version. Every data set has a real mean, right, with a real number, and it has a real standard deviation. Well, what if we could standardize that, where we always set the mean to be 0 and then set the standard deviation to be 1? Then we could just figure out that percentage, and that's what the z-table does. And if I click this, you can actually see the probability. You can use that to calculate the probability. So again, if I slide this over, you can see the z-scores for each one of these, and we're going to practice this as we go through the unit changes and also the probability changes as well. Okay, if you didn't have the z-table, again, you would have to do some pretty intense calculus in order to figure out the area underneath this curve. And if you do continue in math, like maybe you become like an actuary, which you analyze risk and stuff like that, we have many probability density functions, not just this one. It could be different depending on the situation, and you answer many questions by calculating the area underneath the curve, because by definition, the area underneath all probability density functions, the area underneath the curve is 1, standing for 100%, right? And so then you can calculate specific slices of that area to come up with other probabilities, okay? All right, so what does the z-table look like? Well, it looks a little daunting at first, but here we go. Blow this up. This is actually 2 pages, so but really it stands for the left-hand side of the z-curve, meaning left of the mean. Let me blow this up. Left of the mean is in the middle. And then the other page is the right-hand side. So they're showing you the shaded region. Basically, in order to use this table, you have to understand that they are giving you the probability of the left-hand side of whatever you're measuring. Okay, so yeah, if I have like this z value, which would be a negative z value corresponds to how many standard deviations away it is from the mean. So say the z value was like negative 2.25, for example. How would I use this table? And I was trying to ask, what is like what percentage of the data is to the left of whatever this point happens to be? Well, the first thing I would do is calculate the z value, meaning how many standard deviations away. Then I can use my table, right? So I would say, well, if this is negative 2.25, how do I do that? Well, I'm on the left-hand side, so I'm going to use this side of the sheet. And you start on the left-hand side, and you say, okay, well, this z value is negative 2.25. So I have negative 2.2. And then, depending on the third number, you go along these columns. So this would be negative 2.20, negative 2.21, right? And so this one here would be negative 2.25. So I'm going to go all the way to the right and figure out, well, this one here is negative 2.2 and then 5. So what is the answer? What is the percentage of data that is to the left of this particular value? Well, the probability is 0.0122. And the percentage would be the percentage is 1.22. So 1.22% of the data is over here. And actually, you can answer a lot of questions. Like I could also answer the question, how much is to the right? Well, if this represents 100% of the data or an area of 1, I would either take 1 minus 0.0122 or 100% minus 1.22% to get whatever is on the right. Okay. And again, the other page is really nothing. It's just, okay, well, now we're on the right-hand side, though, so the positive z-values. All right. Again, z is simply just how many standard deviations away we are from the mean. Okay. And it always tells us the probability to, or the proportion, or the percentage, if you convert it to percentage, to the left. Okay. And then you have to maybe do an extra calculation if you're looking for the right. Alright, and I think I have one last one, the normal distribution, which we already discussed. This is the Wikipedia page for the normal distribution. It is massive. If you scroll down there, this is huge mathematics, extremely powerful, and you can, what we're going to do is dip our toe into the pool, so to speak, just kind of explore what this is. But yeah, there's an entire field, massive field of mathematics, which is statistics, and it's becoming more and more important, by the way. So anyway, all right, guys. So go back, and that concludes our getting ready portion for probability and statistics. I'll see you in the next one.